Hello and welcome to Quantum Mechanics Mathematical Foundations Talk 3 Part A. This talk is on the Fourier series and the Fourier transformation. My name is Jacob Hudis, and this is Quantum Mechanics the way I wish it was taught to me. Here's an outline for this lesson. There will be a review of the sigma x basis. The sigma x basis spans the vector space C2. Then I'll move on to the Fourier series, fundamental concepts and key ideas. The fundamental concept is that the complex exponential basis spans the function space L squared. There will be a comparison of orthogonal basis functions and orthogonal basis vectors. I'll have a detailed example of finding the Fourier series for f of x equals the absolute value of x. Then I'll move on to the Fourier transform. There will be an introduction and connection of the Fourier series, and then I'll do a detailed example, the Fourier transform for the function f of x equals the absolute value of x. This lesson is intended to be a complete introduction to the Fourier series and Fourier transform from beginning to end. This is suitable for anyone from advanced high school students to physics PhD students. If you dedicate time to these lectures, you will gain valuable information about quantum mechanics and its mathematical formulation. On this slide, I want to demonstrate that the sigma x basis spans the vector space C2. These two vectors are the sigma x basis. This is plus x, 1 over root 2, 1, 1, and minus x, 1 over root 2, 1 minus 1. These are an orthogonal and complete set of basis vectors. If v is any vector in C2, it can be written as a, which is a complex number, times plus x plus b, another complex number, times minus x. Let's take a look at an example. This is a vector v in C2. One of its complex numbers is I, and the other complex number is 2 plus 0.5i. On this slide, I'm going to tell you what the complex numbers a and b are, and show you that it works out. On the next slide, I'll explain to you how we compute the complex numbers a and b. V is equal to this complex number times the vector plus x, plus this complex number times the vector minus x. I factored out a root 2, and I did that to make the math easier, so the root 2 cancels on top and bottom. And if you do the algebra, you can see this linear combination of plus x and minus x does equal to the vector v. The vector v, I, and 2 plus 0.5i written in the x basis is here. On this slide, I'm going to continue with the example. I'm going to show you how we got the vector components a and b. The orthogonality condition is in the box. The inner product of plus x with plus x is equal to 1. The inner product of minus x with minus x is equal to 1. And the inner product of plus x with minus x or minus x with plus x is equal to 0. This information is contained in the Kronecker delta symbol right here. The orthogonality condition is used to extract the amount of the vector along a given direction. For example, if I want to find out how much of a vector is along the plus x direction, I take the inner product of the vector with plus x. Here is plus x, and here is any random vector in space C2. It's a times plus x plus b times minus x. When I take the inner product, that's a times plus x with plus x plus b times plus x with minus x. We know that this is 0 and this is 1, and so this extracts a, which is the amount of the vector in the plus x direction. If I want to find out how much of the vector is in the minus x direction, I take the inner product with minus x. Let's take a look at an example that we've been looking at from the previous slide. Here's a vector v. If I want to know how much of v is in the plus x direction, I'll take the inner product plus x with v. That calculation is here. If I want to know how much of the vector v is in the minus x direction, I take the inner product minus x with v, and that's this calculation. And what you get is a, the amount of plus x is equal to root 2 times 1 plus 0.75i, and b is equal to root 2 times minus 1 plus 0.25i. Here's the vector v written in the x basis. Now I want to move on to the complex exponential basis. This is a basis that spans the function space of square integrable functions. A square integrable function is a function that behaves well. It doesn't have any jump discontinuities or any asymptotes to infinity. These are an orthogonal and complete set of basis functions. The basis functions are these complex exponentials. It's e to the I. N is an integer that can take on any integer value from negative infinity to plus infinity. Pi, x is a variable. Notice that these basis functions have an L in the exponent, and the value you use for L determines the x domain. Any function f of x can be written as this weighted sum of complex exponentials. In a similar way to how the basis vectors of sigma x span the space of all vectors in C2, the complex exponentials span the space of all functions. Any function can be made up of some amount of this basis function plus some amount of this basis function plus some amount of this basis function, and there's an infinite number of terms in the series. This number, a sub negative 5 is an index, and so this is a complex number that tells how much of this basis function is there. A sub 3 tells how much of the basis function e to the I 3 pi x over L is in the sum. The coefficients, for example, a negative 5, a negative 3, etc., indicate how much of each basis function are in a specific sum. Different functions will have varying amounts of each basis function, just as different vectors in C2 are made up of different amounts of plus and minus x. Here's the orthogonality condition. If I take the integral from negative L to plus L of one basis basis function with another basis function with a negative, you have to put a negative here, complex conjugate, you get 0 if the two basis functions are different, and you get a constant 2L if they're the same function. This is the complex exponential, e to the I n pi x over L. Equivalently, we can write it as e to the I kx over L. The complex exponentials are absolutely fundamental in quantum mechanics. These are the basis functions of momentum, and they're the building blocks for many quantum mechanics potential. This is a plot of the complex exponential. This is the x-axis. This is the imaginary axis, and here's the real axis, and it's a complex vector that winds around this helix. On this slide, I do a comparison of orthogonal basis functions with orthogonal basis vectors. On the left, we have the basis of plane waves, which are the complex exponentials e to the I knx. These are the basis vectors of functions over a domain of negative L to plus L. And you can see L is a parameter in this wave vector. In Fourier decomposition, any function can be written as a sum of these basis functions with coefficients a sub n, indicating how much of each basis function is present in the sum. On the right, we see a basis of vectors in C2, specifically the sigma x basis. Here, any vector can be decomposed into a linear combination of plus x and minus x. Any vector in C2 can be written as some amount of plus x plus some amount of minus x. Any well-behaved function can be written as a linear combination of these basis functions. There are two basis vectors for this that span the space C2. There's an infinite number of basis functions that span the function space. The orthogonality condition is shown for both cases. For the plane waves, the inner product of different basis functions is 0, and the inner product of basis function with itself is the Kronecker delta. For the sigma x basis, the inner product of different basis vectors is 0, and the inner product of basis vector with itself is 1. If I know some vector v, and I want to know how much of that vector is in the plus x basis, I take the inner product of plus x with v, and that tells me a. And if I want to know how much of the vector is in the minus x basis, I'll take the inner product of minus x with v, and that would give me b. In a similar way, if I know some function f of x, and I want to know how much of that function is in a given basis function, so if I'm looking for a sub n, I can calculate a sub n by doing this integral. The n, I take the integral of e to the minus I n pi x over L. This n goes with this. So if the n was 2, then this would give me a sub 2. If this n was 4, this would give me a sub 4. I'm going to do detailed examples of this coming up very shortly. Now I'm going to formally introduce the Fourier series. The basis functions f sub n of x are equal to e to the I n pi x over L. This is often written as e to the I k sub n x over L. Any function can be written as a linear combination of these basis functions. So a function f of x can be written as a0, some constant term, plus a1 e to the I 1 pi x over L, plus a minus 1 e to the I minus 1 pi x over L, plus a2 e to the I 2 pi x over L, plus a minus 2 e to the minus I 2 pi x over L, and so on. This sum goes on to infinity, and these coefficients, a0, a1, a minus 1, a2, a minus 2, those tell you the information about the functions. Different functions will have different coefficients. This constant term in the Fourier series represents the average of the function over one period, and if you know the function f of x, you can use the orthogonality condition to determine a sub n, where a sub n is how much of that function is in the nth basis vector. Are you in need of a great physics tutor? Dr. Hudis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. On this slide, I'll do an example where I use orthogonality to determine a3, the coefficient of the eigenfunction for n equals to 3. This example will help you understand this formula, which allows you to extract an, how much of the nth eigenfunction is in the sum. To begin, I'll take the integral of the left side of this equation, so the integral from negative L to L of f of x, and then I'm going to multiply it by e to the minus I 3 pi x over L. The reason that there's a 3 here is because I'm determining the coefficient a sub 3. Whatever I do to the left side of the equation, I have to do to the right side of the equation. Take the integral here times the same phase factor. The integral can go inside the sum, and down below here I've written several terms of the sum. This sum is an infinite sum. It has an infinite number of terms. I want to determine a3. In order to determine a3, I use the orthogonality. The orthogonality condition is that the integral from negative L to L of two of the basis functions equals 0 if they're different basis functions, and it equals to a constant 2L if they're the same. On this side of the equation, there's an infinite number of terms. Each term has an integral in it. Every one of those integrals goes to 0 except for one, and that's because the orthogonality condition. And the one that doesn't go to 0 is the one for n equals to 3. That leads to this formula, and this formula shows how you extract a3 for a given generic function. I want to make a brief note about real versus complex numbers in quantum mechanics. First of all, complex numbers can always be represented as two real numbers. The complex exponential form simplifies mathematical operations such as differentiation and integration, making calculations more manageable. It is possible to work with quantum mechanics using only real numbers, but that would complicate the mathematical formulas. Here's the Fourier series using only real numbers, and here's the Fourier series using the complex exponentials. I think that this was probably discovered after Fourier discovered this. This is the way we do it in quantum mechanics because it simplifies the math, although complex numbers, for some reason, seem to be very confusing. Now I do a detailed example of finding the Fourier series for the function f of x equals the absolute value of x. This is the function plotted. This is y equals the absolute value of x. I know any function can be written as a linear combination of the basis functions, these complex exponentials. The coefficients can be obtained through this formula. A sub n is 1 over 2l, the integral from negative L to L, of f of x, e to the minus n pi x over L. In this specific example, I replace f of x with the absolute value of x, and then I need to compute this integral. The answer for this integral is here. For n equals odd, a sub n is negative 2l over pi squared n squared, and for even n, a sub n is equal to 0. To do this integral is involved. I don't want to bog down this portion of the talk with a long integral. These two slides show how I evaluate the integral using integration by parts, and the end result is right here, where a sub n is negative 2l over pi squared n squared for odd n, and a sub n is equal to 0 for even n. On this slide is the Fourier series for the function f of x equals the absolute value of x. This is how you get a sub n. I know that a sub n is equal to this, so a sub n is done. You should also know that because f of x is a real function, any real functions satisfy the property where an equals a negative n complex conjugate. In this case, an is real, but as you can see, a1 equals a negative 1 because it's squared. a2 equals a negative 2. an equals a negative n because negative n squared equals positive n squared. And that's always going to be the case for real functions, where there's this relationship between an and a negative n. Let's write out the full Fourier series for the absolute value of x. Of course, there's an infinite number of terms. I can't write them all. This is the n equals negative 5 term. I plug in negative 5 to n. Negative 5 squared is just 5 squared, multiplied by e to the minus I, 5 pi x over L. The negative 4 term is 0 because all even n's are 0. The negative 3 term, this is the coefficient of the negative 3 term. This is the negative 3 basis vector. At the end of the day, this infinite sum is equal to the absolute value of x. This is the Fourier series for the absolute value of x in its full glory. We're done finding the Fourier series, but what I want to do now is plot the Fourier series and compare it to the function the absolute value of x. To plot the function, we know it's a real function, so it makes sense to group terms of positive and negative n values. Whenever you're doing the Fourier series of a real function, for example, the absolute value of x or anything without complex numbers, these terms are always going to give you sines or cosines, and you'll always be able to write the function in terms of real sines or cosines. By writing the function this way, it allows us to plot it easier. It does not leave it in the important form of the sum of complex exponentials, but it does allow you to plot it easier. So after some manipulation, this is the Fourier series for the absolute value of x that we already worked out. It's just written in terms of cosine functions, which we can do in this case because it's a real function, and this is going to help us plot it a little bit easier. Now I can go and plot this. Now I want to do a comparison of the Fourier series approximation with the actual function. So first of all, I'm doing an approximation because I'm just taking one term, the n equals 1 term. I guess I'm taking two terms, the n equals 0 and the n equals 1 term. I'm also setting L equals to 1. This is the plot of the Fourier series approximation for n equals 0 and 1. Here I have the Fourier series approximation, and this is plotted against the actual function y equals the absolute value of x, which is in the dashed blue line. You can see they're already pretty similar even for the first two terms. If you take every n, not just n equals 1 as we did here, the approximation becomes an identity. And here I'm just taking some more terms. So here I have the 0 term, the 1 term, the 3 term, and the 5 term. And as you can see, when you add in more terms, the approximation becomes more and more like the function, and eventually it's no longer an approximation, it's an identity if I took infinitely many terms. On this slide, I want to discuss how changing L affects the Fourier series. And in fact, when L gets very large, the name changes from Fourier series to Fourier transform. This is the first 3 terms in the Fourier series for the absolute value of x. This function has L's in it, and that's because the complex exponential has an L in it. L represents half of the function's domain being approximated by the Fourier series. The series approximates a function over a domain of x values from negative L to plus L. So in this case, if I were to replace L with 1, then this represents the absolute value of x between negative 1 and plus 1. Beyond this period, the function repeats, resulting in redundant information. This is only representing the absolute value of x between -1 and +1, although the function, the Fourier series, takes on all values of x, so it just repeats that over and over again. In reality, the absolute value of x has a domain which takes on all real numbers. This is a plot of the absolute value of x, and it goes on for infinity in both directions. So if I were to replace L with 1, then this would give me the absolute value of x in the Fourier series between -1 and +1. But if I was interested in writing a series for the absolute value of x over a larger domain of x values, I'd need to make L larger. And if I wanted to write a series that represented the entire domain of all possible x values for the absolute value of x, or for any function in that matter, I'd have to make L equal to infinity. When L goes to infinity, then it switches from the Fourier series to the Fourier transform. We're going to be discussing that shortly. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics? Dr. Hudis can help. Visit acephysics.org and schedule a lesson today. This is a few terms in the Fourier series of the absolute value of x. On this slide, I've plotted this for different values of L. So for example, if I plotted L equal to 3, then this solid line is the function, and this represents the absolute value of x between -3 and +3. When L is replaced with 2, it gives this function, this dotted line, which is the absolute value of x between -2 and +2, and when L is 1, you can see it's like that. L is the domain of the function that you are replicating with the Fourier series. Finally, we're going to move on to the Fourier transform, and this is probably the most important formula in all of quantum mechanics. Any periodic function can be made up of a sum of basis functions, we know this. These are the basis functions. This is from the Fourier series, e to the I n pi x over L. It's customary to write a wave vector kn as n pi over L, and then you can write the vector Vn as e to the I knx. These two are identical. As L approaches infinity, the Fourier series transitions from a sum into an integral form, and this is called the Fourier transform, and the set of k values transforms from countably infinite to uncountably infinite. Consequently, the values of k become continuous, spanning every conceivable value. So for example, if L is equal to 1, then delta k is equal to pi. If L is equal to 10, delta k is smaller. Now it's equal to pi over 10. If L is equal to 1,000, delta k is equal to pi over 1,000. And if L goes to infinity, then k takes on every possible value. This is slide 2, discussing the Fourier transform. On this slide, I compare the Fourier series with its close relative, the Fourier transform. I'm also going to introduce formally what the Fourier transform is, which is on the left side of the page. This is the Fourier series, and this says that any function can be written as a sum of these complex exponentials, where a sub n tells how much the complex exponential there is for the given function. This is a formula using orthogonality that allows you to calculate a sub n for a given function f of x. So a sub n is equal to this integral, and once again, a sub n tells you how much of the complex exponential is in the given function f of x. Over here is the Fourier transform. I want you to notice that these two expressions are almost identical. There's a constant term, 1 over the square root of 2 pi. It does have some significance, but it's just a constant term, so for right now, just ignore it. And if you notice, this is a complex exponential, e to the ikx, and this is the complex exponential, e to the ikx. A sub n tells how much of the complex exponential is in the given sum for this function. Phi sub k tells how much of this complex exponential is in the given integral, which is also a sum. An integral is a sum for this function. And by the way, this is a function of k. A we have indexed as n, but k is equal to n pi x over L. So this could be a sub k. You could just as correctly write this as a sub k. So don't get confused that this is a function of k and this is a function of n. It's just in this case, L is finite, while over here L goes to infinity. And as I said before, this is a formula that allows you to calculate a sub n using orthogonality. And this phi sub k is a function which tells you how much of each one of these complex exponentials are in a given function. And the orthogonality condition in this case would be called the inverse Fourier transform, or f inverse, and this allows you to get phi sub k. This is a formula for phi sub k where you plug f of x in. For a specific f of x, you get a specific phi sub k, and that phi sub k tells you how much of this complex exponential is in the given function f of x. And I'll do an example coming up in 2 slides. The point of this slide is just to remind you that the integral is a sum. The Fourier series is this sum. It's the sum of complex exponentials. And the integral, the definition of the integral from the fundamental theorem of calculus is that the integral is also a sum. So the Fourier series is a sum of complex exponentials, and the Fourier transform is also a sum of complex exponentials. On this slide, I'm going to do a detailed example of the Fourier transformation of the function f of x equals the absolute value of x. This is the definition of the Fourier transformation. Phi of k tells you how much of each complex exponential is in the sum. The Fourier transformation is writing the function f of x as an infinite sum of all these complex exponential basis functions. It's just like the Fourier series, but now these k's take on every values, not just discrete values. In order to get phi of k, which tells you how much of each one of these complex exponentials is in the sum, I use the inverse Fourier transform. This is using the orthogonality condition, and this is the formula for the inverse Fourier transform. And when I replace f of x with the absolute value of x, I used MATLAB to help me compute this integral, and this is the end result. What we get is phi of k is minus the square root of pi by 2 times 1 over k squared. This is the Fourier transform for f of x for any function. And if we want to replace f of x with the absolute value of x, then phi of k has to be replaced with this function. This is an expression for the absolute value of x over the domain of all real numbers. L is equal to infinity. So for example, if k is equal to 4, you replace k with 4, and then the complex exponential is e to the I 4ix. And if you put 4 into this function, then this is related to how much of this complex exponential is in the sum of the absolute value of x. If you replace, when k is 2, the complex exponential is e to the I 2x, and then there's more. You can see phi is the absolute value. Phi is a larger number, so there's more of that complex exponential in the sum than there was for k equals to 4. These phi of k are related to the weighting of the complex exponential with wave vector k in the exponent. This is the whole thing. The integral is a sum. These are the complex exponentials, and these are the weighting factors for each complex exponential with wave vector k. This is a plot of the absolute value of x between negative and 10 and 10. Of course, it goes on for infinity. And this is the inverse Fourier transform, phi of k, the weighting function for each of the complex exponentials. And you can see that it's very small for k's that are outside of the range of around, almost all the k's are between 1 and negative.